All right, so good afternoon, everyone, and thank you for attending this talk. I won't be talking about LLMs today. I won't be talking about memristors. I won't be talking about learning, but just good old analog CMOS circuits. And I want to take you on a little journey to revisit mismatch in these analog neurons by looking at the dynamics of their inputs. So let's plant the scene. Why do people love analog neuromorphic hardware? Well, here on the right side, you have the current to gate voltage curve of a transistor, of a CMOS transistor. And when you work with analog hardware and subthreshold analog hardware, we like to work, in the left region of this curve, which is the subthreshold regime, where you have a nice exponential relationship between current and voltage, and you also have ultra-low currents, nanoamps, picoamps, or even below. And this exponential slope allows you to very naturally implement the dynamics of a neuron, the spiking dynamics of a neuron, and they offer you all these nice properties, so the ultra-low power regime, as I mentioned, the ability to do in-memory computing, massively parallel, and to use spikes, not clocks, to do fully asynchronous and even-based computation and communication. This is great, right? But why is not everyone doing this? Why is there still people doing digital and using the strong inversion regime? Well, because when you work with this analog hardware, you face device mismatch issues. What is mismatch? It is the small variations that occur during the fabrication of transistors that will slightly change the threshold voltage, slightly change the slope of your curve. And well, I told you there was an exponential slope here. And so small changes in the voltage characteristics will lead to large changes in your currents and your neuron parameters. So okay, you might say, that's not great. That's a fundamental obstacle if you want to do reliable analog computation. And when you look not at one transistor, but at a neuron that's using 10, 20, 30, or maybe more transistor, this is the kind of picture you get if you just give it a DC input and you look at the spike times of a neuron. First of all, within one neuron, you can see you have some jitter. So across different trials, if you give it the same input at the same time, your spike times will not be aligned because you have some noise that accumulates over time, and the longer the trial goes on, the worse it gets. But it gets even worse when you look at two different neurons that are mismatched, as I explained earlier. They're spiking at different frequencies because of all these changes in parameters, and you're not really getting anywhere. There's no coherence across the population. And that might bother you if you think about applications like coincidence detection, sensory encoding, or even motor control, where the timing variability due to mismatch can really degrade the performance of your neuromorphic system. So we're in this kind of struggle, but biology also has these same issues. Neurons are completely different in your brain. There's degeneracy, which means that different neurons can have the same behavior with different parameters, and then you can have neurons that have the same parameters, but different behaviors. Yet, biology is just fine with that, right? As we can all attest as being alive and well in this room. And that was something that triggered this experiment by Meinen and Sernowski some 30 years ago, where they took a cortical neuron and they stimulated it with a DC input and did a few trials, and they obtained exactly what I showed you earlier. There was no coherence between the spike times across different trials. But then they had the idea to take a time-varying input. They took white noise, they froze it across different trials, so they were using the same seed. And what did they get? Well, across trials, the spike rasters here almost look like vertical lines. There was excellent reproducibility across the different trials. And so this made us think, okay, this works in biology. Why not on our silicon neurons? So we took a silicon chip with some, well, there were 16 neurons, which is not a lot, but enough to make this point, using a mixed feedback model that is able to do neuromodulation between spiking and bursting, which I will use later to show something interesting to you. And we tested a bunch of different stimuli. We had the DC stimulus as a baseline, but we also used band-limited white noise, filtered white noise, sine waves, Poisson spike trains, all kinds of signals that have some kind of richness in their frequency contents. And to characterize the reliability across trials and across neurons, we use the metric called the spike distance, which tells you how close two spike trains are to one another. And if you take, it's a metric between 0 and 1, so we just define the reliability as 1 minus the spike distance. And as far as I'm aware, this was the first time that someone tried to reproduce this experiment from Mendolia Sosnowski on physical silicon CMOS hardware. And let's see how it turned out. Well, thankfully for us, we showed that, yes, this works also on hardware. If you take one neuron in different trials, as you increase here the stimulation frequency, or the frequency content, or the bandwidth of your stimulation, depending on which signal it was, we observed much greater reliability. You can see that once you get to higher frequencies, the jitter between trials that you see in the blue raster on the bottom is mostly gone. And looking at all the neurons in the population, on the top right here, you see that all the curves, the reliability curves are increasing. The bursting one is decreasing a little bit, and that's interesting, and I will come back to it later. Is it noise as a resource? I don't think so. I think it is simply using your neuron in two very different ways. When you have a DC input, your neuron is just oscillating on its own, on its limit cycle. Right? You just give it an input, and it fires, resets, and so on. But when you have this frequency-rich signal, the stimulus is just pushing the neuron above and below the threshold and driving your neurons. So that's one half of the equation. The second half of the equation is more of a working hypothesis so far. These mixed feedback neurons that we are using have a property that is called post-inhibitory rebound. So they have a resting level, which is a non-zero input that still doesn't produce spikes. But when you hyperpolarize, so you remove this input, this non-zero input, and then you go back to the resting level, the neurons will produce either one spike or one burst as a transient response. So what if this is a second threshold, kind of? You have your excitability threshold, but you also have a lower threshold once your input goes low enough to hyperpolarize your neuron. This could also be a second source that triggers events and that contributes to this increased reliability score. I have been talking to you about a single neuron so far. I promised you mismatched, I promised you populations, but I've only been showing you single neuron results. So now, what happens when you look at the population of mismatched neurons? Well, we hope that it works, right? Otherwise, this would not be what I promised you. And well, I think the results kind of speak for themselves, where you have on the left a DC stimulus, and you see not only the jitter between trials, but that across different neurons. So the orange and teal neuron here are two different neurons. And well, they're firing at different frequencies, so you don't really ever have agreement in the spike times, because they work again as a limit cycle with their own internal dynamics, their own parameters, and mismatch dominates. But once you use these, time varying inputs, now, well, you could almost draw vertical lines across all the trials of all the neurons, and it just looks way, way more reliable. You wouldn't know that there is so much mismatch when you were using this DC stimulus. And as I explained earlier, this is because the neurons are now being triggered by the input and going above and below their excitability threshold at the same time. Let's look at statistics for the whole population. Well, you can really see, so this is the pairwise timing variability matrices in the population, and you can really see the non-diagonal elements, which are the different neurons, light up once you increase the frequency of your, or the frequency contents of your inputs. So, oh yes. One thing that's interesting to me is that when you look at benchmarks for mismatch and mismatch analyses, people usually use some kind of DC signal, or they use some kind of spike trains that will saturate your synapse at a certain level, and what your neuron is seeing is essentially a DC input. And that seems over-dramatized, because when you're actually using neurons in the real world, your environment is changing, your signals are changing, and so I think this might be closer to real applications, and when that mismatch might be over-defined in some cases. Now, I told you, I promised you I would come back to this drop in performance of the bursting neuron, and that is another interesting result that came with this experiment, is that different firing regimes have different receptive bandwidths, if you will. Your spiking action is mostly created by a bistability between a fast and a slow subsystem in the milliseconds to tens of milliseconds of timescales, whereas bursting is created with a bistability between a slow and an ultra slow that is about 10 times slower subsystem. So what I think is going on here is that at low frequencies, first you have inputs that are too slow to trigger spikes reliably, but then as you go beyond what the internal timescales of the neurons are, the neuron's just too slow to respond, and that's why you get this high frequency drop-off. So let me recap the contributions from this talk. First, we showed that within a neuron, time-varying inputs can transform them from unreliable autonomous oscillators into robust event-triggered systems. We showed that not only for one neuron, but also across a population, where we showed that shared inputs can synchronize mismatched neurons without any calibration, without any coupling, without parameter tuning. There's no synapses on this chip even, so it's really coming from the input dynamics. And third, we showed, or we hypothesized that the excitability timescale was acting on the bandwidth of the neurons. For future works, we want to look at what the accuracy of rate and even time encoding can be, look at some resonance analysis to prove our point 3, and then look at rebounding and non-rebounding models. And I want to conclude with why this matters. First of all, we managed to get robustness to mismatch without any calibration, without layout optimization, without any active compensation circuitry. By using input design as a reliability tool, where choosing an appropriate input bandwidth can substitute for these complicated hardware compensation techniques. We suggest that event timing encoding might be a reliable alternative to rate coding in some cases when you care about precise spike times rather than frequencies. And finally, we offer neuromodulation as a bandwidth control to tune the receptive bandwidth of a system. So if I had to summarize my message in one sentence, would be, let's use analog neurons for what they're good at, which is dynamic inputs and even time encoding. And I want to leave you with one open question, which is, when you look at a paper and it has some mismatch characterization, and you see that they're using DC inputs, is that fair? Does it matter for you? Do you need to care about your application? Maybe. Thank you for your attention.
Yeah, thanks a lot for the presentation. We are perfect on time, so there is time for questions. So please step up, go to the microphone if you have a question.
Hiya, thanks for the talk. I was just meaning to ask, is the noise the same across every trial?
Yes. So I try to avoid using the word noise because I think what matters here is the time variation of the inputs and not so much the fact that it is noise. That's also why we use pure sine waves or Poisson spikes.
So you use like a random like seed state?
Yes.
And then
The seed stays the same across all trials, yes.
I see. How would you expect the results to differ if you use, say, different, well, if you made it like truly random across every trial?
I would expect it to be completely
Asynchronous.
unreliable. Yes, completely asynchronous. Because the point is, if you have a signal coming to different neurons at the same time, no matter how random that signal may be, they should react with the same spike times.
I see. Thank you very much.
Thanks. Inspiring talk. I was wondering, do you have a hypothesis whether there is a differential effect of excitatory frozen Poisson input versus inhibitory frozen Poisson input?
That is something we are about to try. When we use the Poisson spikes as our inputs, we did a mix of excitatory and inhibitory. And one thing we would like to explore is to compare this mixed feedback model, which has rebound, to something simpler like a lift neuron, which doesn't have rebound. That is still a question that is in the air for us, but definitely something interesting too.
Thanks.
Nice presentation, Royce. You know that I'm working on a similar topic, and I would like your opinion about the meaning and the relevance of this frozen white Gaussian noise input, especially at the light of Sunday's tutorial. Do you think that somehow the white Gaussian noise could be a nice approximation for the joint contribution of preceding neuronal excitation? What do you think?
That's an excellent question. And when I look, let me go back. When I look at some example of a signal like this one, which is low-pass filtered white noise, it is true that you could imagine getting this kind of signal very easily from input spikes being integrated into a synapse. So I do believe that it is a relevant type of signal, yes. Thank you.
Okay, other further questions? If this is not the case, we can thank our speaker once more.